Koji Fujiwara, which is going to talk about something like that, a uniform exponential growth of discrete subgroups on Hadamard manifolds.
Thank you very much, David. Thank you very much for the invitation to the organizers. And so I have known Misha for a long time. I met him in many places like Salt Lake City when I was visiting Laden, and also he was a frequent visitor at Max Planck Institute in Bonn, and I used to visit there a lot. And then so it's great to know him for such a long time. This talk is about the joint work with Emmanuel Brogard. And it's going to be about exponential growth for discrete subgroups on Hadamard manifold. But let me start with the definition of a growth rate. So suppose you have a finitely generated group, and then if you are given a finite generating set, then so S to the n, it means ball of radius n. So it means ball of radius n in the Cayley graph of GS. And then you count how many elements this set contains and take the nth root of it and take the limit. So limit always exists, and this number I write EGS and call it growth rate. For this pair. And as you know, if there exists a finite generating set S for G such that the growth rate is bigger. First of all, so this growth rate is, at least 1. So if the growth rate is bigger than 1, is one generating set, then you say G has exponential growth. And of course, this number depends on the choice of S, but if this is bigger than 1 for one generating set S, then it is bigger than 1 for any other generating set S. But since this depends on the choice of S, makes sense for you to look at the all possible values of EGS and look at the inf for all the finite generating set S for G, which is again at least 1, and it could be 1 even if your group has exponential growth. And I write this number E of G, and I maybe call it minimal growth rate. And if this number is still bigger than 1, then people say that G has uniform exponential growth. Okay. So this is a standard definition terminology you must know. Now let me talk about the pi 1 of a Riemannian manifold from the viewpoint of growth. In particular, non-positive curvature. And I like to recall the classical theorem by Milnor, published in 1968, that says if M is a closed Riemannian manifold. In compact, no boundary, Riemannian manifold of negative sectional curvature. So in this talk, I use K to denote the sectional curvature. So we assume this is negative. Then pi 1 of M. So first of all, this is a closed compact manifold. Therefore, this is finitely generated. So it makes sense for you to talk about the growth. And then he says, and has exponential growth. Yeah. So I think dimension. I think that this too. Okay. Yeah. Okay. So let me outline his proof. So first of all, he looked at the universal cover with a Riemannian manifold M. So M tilde. So this is again Riemannian universal cover. So it has the metric and the sectional curvature. So in the universal cover, if you look at the ball of radius r, I fix the base point x here. In the universal cover, I look at the ball of radius r and the compute the volume. Well, I don't compute. I look at the volume. For the ball, then this grows exponentially on r because so curvature in the manifold M is negative. Therefore, in M tilde it's also negative. But more importantly, it's not only negative, but it's bounded away from zero. Okay, so it's square. This part is important. So let me repeat. So this is compact. So this is negative, and it's continuous. So it's bounded away from zero. That means there is a constant, this negative constant, which gives upper bound. Okay. Now, by some comparison geometry, so in real hyperbolic space, you know this ball grows exponentially. Therefore, if it's more negative, then this grows even more faster. So it grows exponentially. So that's the first step. Now, he uses this famous Milnor-Schwarz lemma. Is Qi to the pi 1 of M. Sorry, because it acts co-compactly and properly. So this is Qi to pi 1 by Milnor-Schwarz lemma. Okay, now here you go. So that means since balls in here grows exponentially, and pi 1 is Qi to this space, therefore ball in here grows exponentially too. Balls in pi 1m grows exponentially. So this is the end of the proof. Okay. Right. So it's before geometric group theory, but it's kind of one of the beginning of the geometric group theory. Now I'd like to state record another result much later, much more recent, which is more relevant to my talk due to Besson, Courtois, Gallot. Published in 2011. So let X be a n-dimensional Hadamard manifold. So this means it's a simply connected Riemannian manifold of non-positive curvature by definition. Complete, I should say. With the curvature constraint, this, okay. It's a pinched negative curvature. I always normalize the upper bound by -1, so, but also there is a lower bound, minus a squared. Then there exists a constant c depending only on the dimension and this lower curvature bound. So I like to stress that this constant doesn't depend on the choice of x as long as dimension n and this curvature bound such that if you have any finitely generated discrete group G in the full isometry group of this Hadamard manifold X, then either G is virtually nilpotent, so in that case it has a polynomial growth, or it has exponential growth, but not only that, it has uniform exponential growth. Oh, I should say this is the right. So this is a very strong result because not only this lower bound, there's a growth, a lower bound with growth, not only not depending on the choice of S, and not only depending on the choice of G, but also doesn't depend on the choice of X as long as it satisfies this assumption. It's a very uniform result. Okay, so the lower bound C and A does not depend on S, G, X as long as it satisfies this property. And I like to make a comment. So the comment or remark is that by now probably you wonder if you can find so what is a common way for you to show that the growth, the growth is exponential or uniformly exponential. So that's one way is to find say free subgroup or free semigroup somehow quickly. So, and then for example, Milner didn't, so as you see, didn't use a kind of a group structure. He didn't try to find a free subgroup in the pi 1 of m. And also, it's a common abbreviation, let me call it BCG. They also didn't find a free subgroup or free semigroup in the pi 1. They did not find a free group or free semi group in pi 1 of m. Okay? So what I like to as a kind of introduction, I'd like to state one theorem. Which is published in 2021. After we saw this paper, so we managed to find a free semigroup in the pi 1. So let me write the same. Oh, it came in. Wow. Same setting as in Besson Kyoto Garo. So we could exist some constant, again depending on the dimension and the lower curvature bound, such that so any S are finite generating set of G. If you look at the ball of radius P, this bound exists two element F and G such that F and G generate free semigroup. So existence of a free semigroup in this bounded ball gives a nice lower bound of the growth. So growth is at least 2 to the 1 over B. So growth of the same rank 2 semi-free group is 2, because every time you can use either F and G. So growth is 2, but it's not in S. It's only the B ball. So the growth rate becomes a little worse. So this is so I don't know which number is better, but existence is important. And so we give another proof of this exhibiting free semigroup. And of course, you wonder if you can find F and G quickly. When I say quickly, quickly means some bounded radius ball. Then if I bound this radius, I usually say I can quickly find two elements F and G. So you wonder if you can quickly find F and G which generate a free subgroup. We couldn't do. But then Misha with two collaborators, and one of them is Dave, the first speaker, proved the following. So theorem Kapovich and Liu. So this is published in like so before us. So again, X same as 4. Then exists D, another constant D, such that for any two element F and G in the isometry group of X, and they assume, I think they assume that F and G are non-elliptic, and if you take those two elements as a generating set for this group, I mean, in other words, you look at the group those two elements generates, and suppose it's not but virtually nilpotent, then indeed there is a two element P and Q quickly S to the D such that they generate free group of rank 2, not just a semi-group, free group. So in particular, E of GS is bigger than 3. So the free group rank 2 has a growth rate 3. But since it's only in S to the D, so the growth rate becomes like this. So for this kind of theorem, people say uniform Tits alternative. But I like to point out, I'm curious, Misha was aware, so you don't need this non-elliptic assumption, then it's a kind of final result, because look at our theorem. So the given same setting, we can produce F and G quickly, which generate a free semigroup. In particular, they are not elliptic. So I just plug in our F and G to this, so I don't have to sim this. And so I just want to say this is not really necessary. Okay. Anyway, so this is kind of a introduction, a long introduction. Now let me talk about the main estimate I like to present you. But before that, I again mention background results. So it's somehow better estimate.
Sorry?
Yes.
In the last theorem, you assume that G is discrete.
Oh yes, yes, yes. Yeah. So okay, sorry. X and so let me say X and G same. Yes, yes, yes. Yeah. Same. I should same setting. Yeah. Yes. Better estimate. So let's talk about hyperbolic groups for a while. So let G be a non-elementary hyperbolic group. So Gromov shows that there exists a free group inside of it. Therefore, it has so G has exponential growth. Okay. And then after this, Kubi proves that and indeed he can find this free subgroup quickly. So so uniform Tits alternative holds for G. So G has he proved this is bigger than 1, showing uniform Tits alternative for the hyperbolic group. So I'm tempted to ask a question because I mean this is not my question. I like to recall the question. So those theorems are not only for one group G but a family of groups. So it's natural for you to ask if non-elementary hyperbolic group is uniformly of exponential growth. So is there constant C such that any non-elementary hyperbolic group, this minimal growth rate is at least C. So this is all. Sorry, this is. So this seems open. Good. Right. Now, for a hyperbolic group, something better is known. which is due to Artz-Saber and Lisenok. So published 2006. So let G be a non-elementary hyperbolic group. Then there exists a constant A positive such that any finite generating set of G, the growth rate is at least A times the size of S to the eighth. So this is the estimate they got. So the point is, this lower bound grows if the size of the generating set grows. Yeah. So. Right. So this is yeah. So this is a result I like to discuss today for this kind of Besson-Courtois-Gallo setting. For some reason, I'm gonna tell you probably around the end of the talk. So maybe I'm tempted to make a comment. So you wonder how A can be taken as large as possible. So the remark, the optimal bound of optimal A is indeed known to be 1/2 for, I mean, let me say it. Optimal A for the part. So I didn't have to use same A here, but so let's just focus on this part and this exponent. Then A for this exponent for free group is 1/2. That's due to Razborov. And then there is a shorter paper by Safin, and also there is a paper by Bottom, and also for hyperbolic groups. That's due to Delzant and then Steenbock. So this is very nice optimal bound, but I don't need this much today. Okay, so let me. So let me state. I like to state two theorems. For state theorem 1. This is not on the archive yet. We have a draft, but not on the archive yet. So let X be an Hadamard manifold of dimension n and the same curvature bound. Then exists a constant A, again depending only on this lower bound and dimension, such that any finite subset, I mean finitely many elements of isometries such that the group G generated by S is discrete on X and also torsion free. So first theorem I assume it's torsion free, and G is not virtually nilpotent, then the growth rate satisfies, has this lower bound. So same as Gunara-Lisenok theorem. Again, so this constant A doesn't depend on G or S or X as long as satisfies this assumption. And one remark is that this torsion-free assumption is necessary. And let me give an example where, with torsions, where this estimate fails. Sorry. Torsion free is necessary. Sorry. So example. So my X is H4, four-dimensional real hyperbolic space, and I prepare Y, which is a totally geodesic hyperbolic plane in this four-dimensional hyperbolic space. So it's just okay. And so first, let Cm be the, so X, this is H4, be the cyclic subgroup order M, which acts as rotations of order M around Y. So let me write a picture. So so this is Y. It is two-dimensional, but the whole dimension. I mean, I can. So this is two-dimensional. So Cm does this rotation. So the codimension is 2. So just rotate, fixing each point of Y. So this is what this Cm does. And also I prepare two more elements. Let G and H, again isometry of X, be elements which preserves Y. So maybe I write a picture here. So now I write Y as really like two-dimensional. Y and it act as a hyperbolic isometry on y. So this is g axis, and this is h, the axis of h. Such that this g and h produce a free group rank 2, which is easy, just to take independent elements and the large translation lengths, then g and h produce a free group of rank 2. But not only in y, but its isometry x. So now I go back to this picture. So g and h is a hyperbolic isometry, but it doesn't rotate. It could, but I just make sure. I mean, I just want to be concrete. So g and h doesn't rotate around y. Okay? So somehow g and h extend trivially to x. Okay. So such that therefore g and h commute with Cm. Yeah. So now I just therefore so now my group Gm is Cm times this F2, which is generated by G and H. So it's a direct product in an isometric group of H4. And my generating set for this one is, of course, I take all the elements in this finite cyclic subgroup, and I take G and H, which generate Gm. So the size of this generating set is M plus 2. Now, what is the growth of Gm Sm? Well, so this is a direct factor, and it's finite, so it doesn't have any effect on the growth. So the growth of Gm in terms of Sm is completely determined by E, this F2, and GH, which is 3. Okay, so now you see a counterexample. So you have a sequence of and of course this is discrete. So you have a sequence of discrete subgroups in isometric group H4 generated by bigger and bigger generating sets. However, the growth doesn't go up. So so this is a counterexample to this estimate if you don't assume torsion free. Okay. So this is this is a little annoying, but it turns out this is a general picture. The point is, if you want to compute the growth of Gm, Sm, you should look at the action of Gm on the hyperbolic 2 plane y, where you really precisely know the growth rate. So groups with torsions. So let me briefly explain what's going on in case there are torsions. X an Hadamard manifold, and if you have a subgroup, discrete, maybe with torsions, And one fact which is used to prove that G contains the biggest maximal finite normal subgroup. The unique maximal finite normal subgroup, which I write n or n of g. So in this picture, Cm is the one. This is the biggest normal subgroup. So since it's normal, you go to the quotient. Okay, so G bar. So right here. So this is in the example. This is Cm. In the example, this is F2. So you have a projection map, and so if you have a finite generating set S, then it maps to some finite generating set S bar for G bar. So this is, in that example, GH. Yeah, and this was. And this map, GG bar, is a finite to one map. Is the kernel of this map, the size of it, to one map. So it again doesn't, if you go to the quotient, the growth rate doesn't change. So the claim is E of GS is equal to E of G bar S bar. Okay? As in this example. Let me further say how in this setting you can find Y. So in that example, there is Y on which you see the essential part of the action. So where is it? So since n is a finite group acting on a Hadamard manifold, so there must be at least one fixed point. So let fix n be the set of common fixed point for all n, element n, or the common fixed points by n. So then, as I said, first of all, this is non-empty because non-positive curvature. And since n is normal, this is G invariant. And now, I'm looking at the manifold. So this fixed point set is a submanifold, totally geodesic. So it's a totally geodesic submanifold in X. Okay? And now, of course, G is acting on this submanifold because this is G invariant. But this is a fixed point for the action of n, pointwise. Therefore, you can also consider this the action of G bar in here. And of course, since the action of G on X is discrete, so let me. So this is Y in the example. This is discrete. And since I take the maximal one, so this action is faithful. So this is the this is how somehow we prove this kind of things. So this is what's going on in general with torsions. Now the theorem. So I write theorem 2. So it's so theorem 1 is a special case. Yeah, same assumption. Theorem 1. So let S be a finite set such that the group it generates is discrete. I don't need torsion free anymore, and G is not virtually nilpotent. Oh. I mean, the order is not great, but exists A, An, maybe different constant. So An again depend only on the dimension of X and the lower curvature bound, such that E G S is at least A times size of S bar, not S, to the A, which is equal to G bar S bar. Okay. So in reality, we apply the theorem, kind of variation of the theorem. I mean, in theorem 1, we assume torsion free. But indeed, as long as this radical, I mean, sorry, normal subgroup, finite normal subgroup is trivial, it's fine. So we apply the variation of the theorem 1 to the G bar, S bar actions on this fixed point set of N, and prove this part, and then it implies this. So this is the general case. Okay, any questions? Now let me explain why we wanted to show this. So I call it motivation. It's a little strange. I say motivation at the end. Simple. And you may have heard this before. So before I state something we prove using this, again, let me recall one theorem. So background. So some time ago, I proved the theorem with Sela that if G is a non-elementary hyperbolic group, then if you look at the following set, so in the beginning I defined the growth rate for G for the choice of generating set. So, but it varies. So S runs over all finite generating sets of G. So let's look at this set. So this is a numbers. This is a subset in R bigger than 1. And we prove that this set is well ordered. Namely, I remind you the definition, any non-empty subset in this set has a minimum in it. Any empty subset has min in it. So inf is achieved in the set. So in particular, this set has the smallest number. So that means for each g, there must be each non-elementary hyperbolic g, there must be some generating set which achieves the smallest growth. And moreover, and also for each number, growth in this set, there are only finitely many generating sets for which the growth rate is this number. Only finitely many S with the growth rate is this number, and up to auto of G. Because if you have a S whose growth rate is R, and if you change S using the an auto of G and get a different generating set, but of course it's going to have the same growth rate. So this finiteness is true only up to the auto. And then in the very beginning of the proof of this theorem, we need this Alexander-Lisenok theorem. So in the beginning, of the proof, we need this EGS is A is to the A. Okay. How do we use it? So to prove this set is well ordered, so what does it mean? It means if you have a descending sequence in this set, it has to stop in finite step. Okay, that exactly means this set is well ordered. So given a descending sequence of growth rate for the group G, so since it's a descending sequence, in particular, the growth rate is bounded from above. Now you have this estimate. So if left-hand side is bounded from above, of course, the size of S is bounded from above. So passing to a subsequence, you can assume that in that descending sequence of growth rate, the size of generating set is constant, so like 10 elements. Now you can use the space of marked groups. Then use the space of marked groups, and then go to a limit group and argue. So anyways, in the beginning, we need this. So having this theorem, we are able to extend this result to the family of groups. So let me just state it and conclude it. So let X be a symmetric space of non-compact type of rank 1. In other words, it's either real hyperbolic space, complex hyperbolic space, quaternionic hyperbolic space, quaternionic hyperbolic plane. And let for each x, Cx be the set of all possible growth rates. So this is E, G, S. So G is it is discrete. finitely generated, not virtually nilpotent, and S is a finite set, and S generates G. Okay, this is a set I like to discuss. Again, this is a sub, and not virtually nilpotent, so it has exponential growth. This. Then this Cx is well ordered. And for each R, only finitely many, not GS, but G bar, S bar, with R is E, G, S, which is equal to E, G bar, S bar, again up to isomorphism among the pair G bar, S bar. Isomorphism means, so you have a group and a generating set. So two pairs are isomorphic if there is a one-to-one map from one generating set to the other, which induces the isomorphism of the one group to the other. Then we call it isomorphism. So for this one, we really need E, G, S is leads to A, constant X, S bar, AX. Okay. So I erased it, but without passing to S bar, we don't have this, but the structure of the argument is exactly the same. So we like to analyze the descending sequence of this set. So since it's descending, E of GS is bounded from above. Therefore, by this estimate, the size of S bar is bounded. But I almost erased some part is there, so we look at the Y in the space X. So Y depends on the G, but it doesn't matter. So that's how we argue. So we really need this theorem too. Okay, I think I stop here.
Other questions?
Sorry, what do you mean by finite? The finite after computation in the isometric group of X. What do you mean by finite?
Up to isomorphism?
I mean, abstract group isomorphism, or up to you mean abstract group isomorphism? Or what do you mean by
Yes. Not in isometric group of X. Yeah. Right.
Isomorphism of G.
Yeah. G bar. G bar S bar. Among G bar S bar. Razvorov type estimate?
Yes.
We don't know. I don't know. I didn't. It's a good question. Yeah.
You think it's true?
What I think? I think so. Yeah. Question could be, so here I use the same. I was lazy. I use the same A, right? But I should have said B times size of S to the A. So maybe A is 1/2, but this one maybe depends. But yeah. Anyway, so answer to your question, yes, but I don't know.
So does these well-ordered sets have elements with no predecessors?
So say it again?
So like an element that has another predecessor. So the type of well-ordered set that you are getting there, do you have like limit points?
We have a limit point. The order type?
Yes.
Okay, at least omega to the omega. So I should have said, so here, the order type is at least omega to the omega, if you know what it means. But of course, this set is much bigger. So for example, each of these sets contains a hyperbolic group. So the set of growth is much bigger. So at least, yeah, it has a limit point, many accumulation points. Yeah.
How important is the lower bound of the curvature? Do you have counterexamples when there is no lower bound? There's no little a.
We need a. So we need Margulis lemma. Okay, we don't have a counterexample, but okay. So I would be embarrassed if I'm mistaken. So for Margulis lemma, I think I need lower bound. Is that right?
Yes.
Right? Yeah. So okay. So definitely we need Margulis lemma. For uniform result, we need Margulis lemma. Upper bound, we need hyperbolicity.
Because in some sense, when you gave the proof of Milner's proof, right? No. There, only the upper bound matters, and somehow the lower you get, the lower curvature gets, the smaller it gets, the growth should increase. So it's a bit strange that this A.
But uniform bound is harder. I mean, Milner is individual, so to have a uniform control, I didn't, yeah, I need it essentially in the argument.
Because it ensures bounded geometries so that you have exponential. Yeah, not more than like Milner will have because of the co-compactness.
So when you look at this psi x for a given space, so there must be a minimum.
Yes.
Is there any hope to compute it?
No.
No.
No, probably no. Of course, I could ask a question, which G and S achieves the smallest?
And that's already very hard.
Yeah, even in dimension. Yeah, so I like to tell that in the closed surface group, it's one hyperbolic group. Therefore, there must be a generating set which achieves the smallest growth, which is unknown. We don't know which one is going to achieve the smallest growth for the closed surface group. So it's hard.
Okay, well, if there are no more questions, let's thank Koji again and we'll meet.